to the stream on countable sets. Last time we looked at cardinality and that took a little bit of effort. Today we're going to build on those ideas of cardinality to look at countability or sets that are countable. So let's first start with a definition on what we mean by countable sets. So firstly, a set is finite if you can find a bijection from a finite set to the set S. In other words, if you can join up the pieces 1 to an item in S, 2 to another item in S, all the way to N, and those are the only connections that you can make, and you sort of hit every single person in S, in that situation we say that S is finite. And we'll say that S is countably infinite if you can do the exact same thing, but this time with all of the natural numbers. So you can you can link up each natural number with exactly one item in S. Everyone in S gets hit, and every item in S gets hit by only one item in N. Here's a quick picture. So here is the natural numbers, for example. We start with 0, 1, 2, 3, 4, and so on. And if you can link them up with items in S, say the first item, well, we'll call this the 0th item, the first item, the second item, the third item, the fourth item, and so on and so forth. And you're able to find a connection to each of these guys. And this connection hits everyone exactly once. Then we call this a bijection from N to S. And in this situation, we say that S is countably infinite. And sometimes we like to compress these ideas together, and we'll say that S is countable if it is finite or countably infinite. So countable is sort of the umbrella term to describe this sense of smallness. Of course, the infinite case still presents a little bit of trouble for us, but it does thankfully give us some nice properties to work with. Any infinity that's sort of bigger will be relegated in the study of set theory. So if you want to learn more about all these other cardinal numbers, if you would, feel free to delve into set theory a little bit more. So the first claim, just to warm up, is that the collection of natural numbers is countably infinite, which sounds a bit strange, like of course it is. But here we are using countably infinite in the technical definition of finding a bijection. So here's the question, and let's quickly illustrate this idea. Are we able to find a bijection that is able to link up every item in the natural numbers with every item in the natural numbers? Well, of course, you can use the do-nothing function, and we've shown that the do-nothing function, or rather the identity function, is bijective. And since we have a bijection from N to N, we can conclude that the collection of natural numbers is countably infinite. That's just a really quick sanity check on how to describe the idea of countably infinite. And we can check the same result for a few other commonly used sets. So here's the claim. The collection of even numbers, and sometimes we use this notation, especially if you're heading into abstract algebra, we use this notation. Otherwise, that's not important. The important thing is that we are considering the collection of even numbers, and we claim that this collection is countably infinite. Now, this might be a little bit surprising to you, because if we were to draw out the number line for N is gonna give us 0 to 1, 2, 3, 4, 5, 6, and so on. But however, 2n is only going to give us the even numbers. So it's tempting to think that, wait a minute, if it's going to be 0, 2, 4, and 6, then there is no real way in which I can link the items up. After all, if 0 goes to 0, 2 goes to 2, 4 goes to 4, 6 goes to 6, I can never ever hit the odd numbers. But here's the irony of everything. Nobody insists that the connection needs to be on the same horizontal level, if you would. As long as you can find a bijection, then the thing being bijected is countably infinite. And how are we going to make our bijection? We're going to define our bijection as the times 2 function, if you would. So 1 will go to 2, 2 is going to multiply the 2 to give us the 4, 3 will multiply 2 to give us the 6, 4 will go to 8, 5 go to 10, and so on and so forth. And we can define the function we can define our bijection, so we'll define f from the natural numbers to the collection of even numbers by f of n equals to 2n, and this is a bijection and this tells us that the target set 2n is countably infinite. In fact, you can check this as an exercise as well. You can check that the collection of odd numbers is also countably infinite. And something even more remarkable holds if you can see an interesting pattern. Here is my conjecture, and you can try this as an exercise. Let f from n, let f from R to R be any bijection such that f of n lies inside n. This is just a conjecture, but feel free to check this out. So in other words, I will plug in any natural number and I'll spit out any natural number. Then f of n is countably infinite. Oh well, my pen battery is not working. This is kind of awkward and embarrassing. So we will go for a short break really quickly. How ironic it is. We're only like 5 minutes into the stream and we need to go for a short break. I need to charge this guy. So we'll go for a short break and we'll be back in just a moment. But here's the conjecture that f of the natural numbers is countably infinite. That was rather awkward and embarrassing. We'll be back. Alright, we are back. We have a question. Is the set of countable sets a countable set, or is it an uncountable infinity? We are actually gonna look at that in just a moment. If we consider all of the different countable sets and we put them into a box, we might get something a little bit surprising. And what's even more interesting is the proof for that result. So we're gonna take a look at that in just a moment. Now, prior to the break, which was due to the pepper pencil dying, not because I got tired of cardinality, then I gave this result, which you can try to prove as an exercise. But interestingly enough, we can sort of look at it as relaxed as possible. So if we let fr to r be any injection, then we'll automatically get f of n being countably infinite, and this actually applies to many results. So you can try this out, you can try to prove this on your own, and let me know how you go about it in the comments section, the chat, all that good stuff. But yes, countability simply refers to a bijection from the natural numbers to whatever set you're thinking about. And here's the fun claim. Ideally, if we have two sets and you can biject from one to the other, they are sort of having the same size. So more precisely, in this question, if we can find a bijection from A to B, then if the target set is countable, we should be able to conclude that the input set is countable. So perhaps a picture is more useful at this point in time. So here's A and here's B. And suppose that we can find a bijection from A to B. If we already do know that B is countable, then intuitively we would have that the set A would also be countable, because every item in A, in a sense, is tagged on to every item in B. And that's the fun stuff over there. So let's make a quick proof as to why this might be the case. Now we do know that A to B is a bijection, so we do have a bijection f from A to B, right? That's what the question tells us. Now, if B is countable, so we'll suppose that B is countable. Technically, in our setup, countable here could be finite or countably infinite. We could have one or the other. So we should be careful to distinguish between these two cases. Now, interestingly enough, the logic works the same. So for a start, let's first suppose B is finite, and later we'll see how to modify this proof for the countably infinite situation. In fact, we can just do it this way. So we'll first suppose B is finite, later we're gonna do a simple remodification. Then what this tells us is that if B is finite, we can find some natural number and a bijection from 1 to this natural number to B. If B is finite, then it can be corresponded in a sense to a finite set of natural numbers, and this is a bijection. So what this tells us is that here's another picture to sort of illustrate the point. I'm gonna remove this over here, and we can think of it this way. A can get bijected to B, and we'll call this bijection F. And B can be bijected by the collection of, well, some finite collection of natural numbers. What this tells us is that we should be able to biject the natural numbers to A using the composite function F inverse circle G, because we're going from this set to B, and then we're going from B to A, which requires us to inverse the F. So we need to inverse the F, and this gives us G followed by the F inverse right there. What this means is that F inverse circle G is a bijection from this finite set to A. And since we can find a bijection from a finite set to A, we can conclude that A is finite. And this tells us that if A is finite, then A must be countable, because we allow countable to be either finite or countably infinite. So we've proven the situation when B is finite, and strictly speaking, we need to prove the situation when B is countably infinite. The irony is that the argument is literally gonna be the exact same argument, and I'm gonna show you guys that in just a moment. So if we replaced finite with countably infinite, then the bijection is not from the finite set, but instead from the natural numbers to B. The only difference is that B is not bijected by a finite set, but by all of the natural numbers. That's the only difference. But by that same logic, F inverse circle G will be a bijection from the natural numbers, all of the natural numbers, to A. But that means we can find a bijection from the natural numbers to A, and that tells us that A is countably infinite. And once we have A being countably infinite, we're good to go. Then A must be countable. So I think the better way to summarize this result is to combine these two guys to say that A is countable. So countability is a really nice property. If the target is countable and you can biject into the target, the source must be countable. And in a sense, countable is what math people like to consider the smallest infinity as well. But how do we formalize that in any strict sense? We shall formalize it in this manner. If A and B are sets such that A is a subset of B, in a sense, if B is countable, A must be countable. And I've put the green star over there because this is actually a really difficult result for us to prove. So we're not going to prove that result yet. We're going to prove that later on, and we're going to come back to sort of fill in all of these details. Let's just first get an intuitive grasp of the idea of countability, and then we'll go into the hard work. We'll do the hard work to prove all these results, which, I mean, it should make sense. If B is countable, then the thing that's smaller than B should be countable. I mean, that sort of makes intuitive sense. So we're going to prove these results later on, and these results tend to have rather novel proofs if it's the first time you're doing discrete mathematics. So that will be an interesting question. It will be tied to the whole uncountable infinity question that's currently raised, so stay tuned for that as well. Now, all that being said, suppose we already do have this claim. In other words, here's a picture. Here's A, here's B. If B is countable, and I'm going to abbreviate using these letters, technically when soon. Trust me on this. I've already thought about it. Technically, when you prove the star, you will prove the above question. Yes and no. So the idea is we're going to use the star to prove this result, right? So that's why we're gonna start using this, and we're gonna prove. I mean, I guess that's true, right? That's true. So we're gonna use the star to prove this claim, but we need to come back to prove the star again, right? So there's sort of an application of the idea. So we let A and B be sets. Suppose that we have an injection from A to B, and the idea is this, right? The star tells us that A and B must lie in the same world. Whereas for the claim which we're trying to prove, A and B may not be directly related at all. They might be living in completely different worlds. So A could be here and B could be here. You know, A could be the collection of students and B could be the collection of rational numbers. It may not even belong into the same universe, if you would. But that being said, if we can inject it, and usually math people like to use this symbol, but it's okay, we don't need to use that symbol for injection. If we can inject A into B, we can get A being countable. And the proof is basically using the start claim, but let's just take a look at that. Here's the picture. Before we analyze it, it's good to have a picture. Suppose this is A, and suppose this is B. The idea is that if we can inject A into B, then sort of whatever is the output of the injection would lie inside of B. But if B is countable, then that collection of outputs is countable, and then A itself must be countable as well. So let's first establish the result. So by definition, f of A is a subset of B, right? Because every item in A under the function f goes into B. That's by the idea there. And since B is countable, we can use the start result to conclude that f of A is countable. But how do we use this to prove that A is countable? We need to see something a little bit interesting here, right? So f goes from A to, say, B, but let's define not f, but let's just define a new function g from A to f of A. It is a technicality. I know math people call this the restriction, but it's okay. And we'll define g of x to be equal to f of x for any x in A. Perhaps you can check it for yourself that G is a bijection. That is, it is both injective and surjective. But what this tells us is that G inverse that goes from f of, this is good. This tells us that we are bijecting from A into f of A, but we already know that f of A is countable. And if we can biject into a countable set, the source set must be countable as well. And so we can conclude that if G is a bijection, and you can check that it is indeed a bijection, that A is countable. And that is how we establish this result. Now, why do we put in all that effort? What's the point? I mean, isn't the subset and injection essentially the same idea? In a sense, it is the same idea, but here is the trick. Now, we have a shortcut to determine whether a set is countable or not. A priori, we have to establish a bijection. But here, if we can inject into a countable set, in other words, we can go from, if we can do this, if we can go from A, if we can inject it into some countable set, we can conclude immediately without doing any more work, without even checking that this mapping is bijective, that A is countable. And once we have this shortcut, it allows proving various sets to be countable to be a far more trivial task. So let's take a look at that in this upcoming question. So we are going to claim that n cross n is countably infinite. Now, you can use the same idea to prove that the collection of rational numbers is countably infinite as well. But let's just recap what do we mean by n cross n. So we say that what is n cross n by definition? N cross n is the collection of mn's of pairs such that m lies inside the natural numbers and n lies inside the natural numbers. Now this is taken from the more general definition of A cross B, where A cross B refers to the collection of ordered pairs AB, where A lies in A and B lies in B. So we want to show that this set is countably infinite. And here's how we're gonna do just that. If we want to show that n cross n is countably infinite, we want to try to inject this set into a countable set. That's the idea. So we're going to try to define some injection, and I don't need a bijection in this context. We just need an injection because we've already shown that if you can inject into a countable set, you're good to go. So could we define an injection from n cross n into n? Can we do this? Well, we need to come up with this injection, right? So what's the idea over here? Well, here's the idea that I have in mind, and there are a few ways to go about this. But here's a very sneaky idea that I have. Okay, so here's the point 0, 0. Here is the point 1, 0, 0, 1, 2, 0, 1, 1, 0, 2, 3, 0, 2, 1, 1, 2, 3, 0, 3, and so on and so forth. And here's what I'm going to do. I'm going to map 0 to the number 2 to the 0, 3 to the 0. I use 2 and 3 because they are the first prime numbers. And then I'm going to map this number to 2 to the 1, 3 to the 0. I'm going to map this number over here to 2 to the 0 and 3 to the 1. And in general, for any point, let's just say for example, this point here has x coordinate 1 and y coordinate 2. I'm going to map this point to the number 2 to the 1, 3 to the 2. You might be wondering, but will I miss some numbers in the natural numbers? The answer is yes, we're going to miss some stuff, but it's okay, we just need an injection. So more precisely, I'm going to define f, m, n by 2 to the m and 3 to the n. And now, here is the hard work that needs to be done. We need to check something really, really important here. If we can show that this is an injection, then we can inject from n cross n into n, and we're good to go. So that's our claim. We want to try to show our claim is that f is an injection. If we can prove the claim, then we have found an injection from n cross n to n, and we're good to go. So here's our proof of our claim. Let's establish the formula for an injection. We'll start off by fixing any inputs. And then we'll suppose that the outputs equal to one another. By our formula, we can plug in the values. And something rather interesting happens here, right? Because we have 2s and 3s, right? So every number on the right side must be a factor of the left side and vice versa. But since numbers have the same prime factorization, we can conclude that m1 equals to m2 and n1 equals to n2. And if we can make these conclusions, we can conclude that m1 n1 equals to m2 n2. And this and once we can show that, and we've shown it, this actually establishes that f is an injection, and we're good to go. So since we have shown that f is an injection, we have shown that n cross n is countably infinite. So that's a really neat trick. Now for q, let me give a hint over here. You probably want to biject it into n cross n. That makes your life a little bit easier, right? So that's sort of the ideas that we have over here. You might be wondering where are the integers? Where is z? We're gonna come to z in just a moment, so that'll be fun. So we've already proven this result. That if we can inject into a countable set, then the source set must be countable as well. Now we've used this result to prove that n cross n is countably infinite. And what does that mean? Well, if n cross n is countably infinite, then we claim that A cross B is countable. Now, I'm gonna cheat a little bit here, and I'm only gonna prove the situation when they are countably infinite. Now, some of you might be complaining, wait, Joel, you're cheating. How can you just prove countably infinite? Isn't countable including the finite situation as well? The answer is yes, but we'll get to that. We'll get to that eventually. How do we sort of combine the finite situation, in a sense? We'll come to that later on. For now, let's just really quickly prove the situation when it's countably infinite. And here's the idea. Right? The idea is that A can be bijected into the natural numbers because that's countably infinite, and B should be able to be bijected into the natural numbers as well. So in a weird way, if we can sort of combine the bijection properly, and this is obviously a very informal way of describing it, we should be able to get the product on the right as well. In a sense, it's like equation manipulation. But here's how we do it a little bit more formally. So let's first establish the bijection. So since A is countably infinite, there exists a bijection from A to the natural numbers. Now, technically, we should go from natural numbers to A, but bijections go both ways, so we're good to go. I think we can... Let's use the... Oops. It's a bit technical, but let's just do it this way. Let's just go from natural numbers to A. It's possible. I mean, it's fine. It's not a big deal. Right? I mean, you could inject it too, but it's fine. So, so you can find a bijection from N to A. And similarly, since B is countably infinite, you can also find another bijection. Since B is... I'm just gonna copy and paste, okay? Countably infinite, there exists another bijection, but this time from N to B. So how do we sort of combine the bijections? How do we combine the bijections from N cross N to A cross B? Well, simply, we'll define H to be... Oh, this might be a problem, I realize. I should be trying to inject from A cross B into N cross N. So let's first... it's a small technical difficulty, but it's fine. Let's just very quickly rewrite these statements. Again, bijections go both ways, so things are fine here. We're going to define H to go from A cross B into N cross N by this particular mapping. HAB is going to be equal to, surprise, surprise, F of A, G of B. That's it, right? So A is going to get transferred via F, and B is going to get transferred via G. And once again, all we need to do now is to check that this mapping, let's claim and prove this claim, that H is, injective. Again, we do not need the full power of bijections. We just need injective, we're good to go. And the proof is not too difficult. So let's prove it. And to show injectivity, we'll fix the inputs. Oops, this is a rather awkward and embarrassing. Let's do that again. We'll fix the inputs and then we'll suppose that the outputs are the same. That tells us by our definition that f of A1, g of B1 equals to f of a2, g of b2. And when you compare the coordinates, because corresponding coordinates must equal to one another, we get that f of a1 equals to f of a2 and g of b1 equals to g of b2. But f is a bijection, so if f is a bijection, it's an injection. And if it's an injection, you get a1 equals to a2. Similarly, since g is an injection because it's a bijection, you get b1 equals to b2, which tells us that the corresponding coordinates must equal to one another. The 2 points must be the same. This tells us that the inputs must be the same. So the same output gives you the same input. That tells you that H is injective. And since H is injective, A cross B is injective. Not A cross B is injective. A cross B is countable, because we can inject into a countable set. So the source set must be countable. Countably infinite to be precise. Now, you might be wondering, wait a minute, what about the... this is countably infinite. What about countable? What about just countable without any countably infinites? We're gonna patch that very, very soon. So here's another interesting result, which we will once again prove later on, because it actually takes quite a bit of effort to prove this particular result. So if A and B are countable, then the union of two countable sets must be countable. Again, it sort of makes sense. If you take two sets which you can count, you should be able to count throughout the two sets, right? That's the idea. Surprisingly, it takes a little bit of effort to prove, but we can use this result to establish that the integers are countable. It's kind of roundabout, like why did we suddenly come back to the integers? Well, because if we look at it carefully, the integers is made up of two sets. Firstly, it's made up of 0, 1, 2, 3, so on and so forth. Secondly, it's made up of the negatives of all of these elements. And I put the 0 there because you are allowed to overlap items. We are not insisting that A and B are disjoint. And the first one is basically your natural numbers. The second one can be thought of as, in a sense, negative of the natural numbers, in a sense. But what's more important than the notation is that both are countable. Both are countable. And once we have both being countable, if we take the union of two countable sets, the claim tells us that the union of two countable sets is countable as well. So that's a really neat trick, but that raises the question, how do we prove that the union of two countable sets is countable? We'll get to that later on as well, because the proof over there will take a little bit more effort. It's not too difficult. You basically want to inject into two different parts of the natural numbers, but we'll get to that in just a moment. And strictly speaking, for countable, there is some trickery, right? Because countable can mean finite as well. So we also have to take care of the finite situation. It's kind of irritating, but it is what it is. So we'll prove that later on. But it does make sense. If you take the union of two countable sets, you should get something that's countable, right? So we'll prove that in just a moment. Now, here is the patch that we were talking about. So there was a result earlier on that on countably infinite sets, right? There was this result just now. Let me take a look. Where I cheated. Yeah, this one, this A cross B result on countably infinite. Let's just write that result over here very quickly. If A and B are countably infinite, then A cross B is countably infinite. Right, we've proven that it's countably infinite, but we have not yet proven a situation when it's just countable. And this is where we're going to establish this particular claim, right? So we'll call this one, we'll call that a yellow claim, or rather we'll call this claim 1, and then we'll call this part claim 2. If A, B are countable, again, not worrying about infinity, then A cross B is countably infinite. So here's how we can patch the result. So for proof of the claim 1, if A is countable, it could be finite, it could be infinite, we don't care. Why do we not care? Because all we care about is that we'll define A star to be the set A union with the natural numbers. And here's why we want to do it this way. If A is countable, and then we know that n is countably infinite, therefore it's countable, and the union, well, the union of two countable sets is countable. And at the same time, we also have seen that if the bigger set is countable, then the subset of a countable set must be countable. The logic works that if you have a subset of a finite set, if the bigger set is finite, let's just maybe draw a few pictures here. So there was a result which we haven't proved yet, we are going to prove it later on as well, that suppose you can inject A into B, or more accurately, you can consider A and B as a subsets. We haven't proved this yet, so we'll need to prove this. We've shown that if B is countable, then A must be countable. Because in some sense A is like smaller than B. Now, even more semi-obviously, if B is finite, then anything smaller than a finite set has better got to be finite as well. Correct? But we do obtain the contrapositives from these statements. In particular, for our context here, if the smaller set isn't finite, then the bigger set has to be bigger, right? So it has to be infinite as well. And in particular, A union n is going to be bigger than any of the constituents. So it's bigger, it's a superset in the sense of the natural numbers. But the natural numbers is countably infinite, and therefore A star is also infinite. Now, since A star is countable and infinite, we can conclude that A star is countably infinite. And once we can prove that A star is countably infinite, in other words, any set is going to be, well, any countable set is going to be smaller than a countably infinite set. I think that should make sense. But this is how we can use this to patch our claim 2. So let's prove claim 2. And that is this. Since A and B are countable, you can always find countably infinite sets that contain A and B. You can always find A star and B star that are countably infinite, such that A is a subset of A star and B is a subset of B star. And once you can make A a subset of a countably infinite set and B as a subset of another countably infinite set, the Cartesian product will be smaller than a countably infinite set, which is countable. So therefore, since this guy is countable, using the result that we actually haven't proved yet, A cross B is countable. Right, the subset of a countable set must be countable. So we do have a lot of useful results from countability that we can employ in problem solving. But we have a few claims that we are going to need to justify. In a sense, countability is the study of like the smallest infinity. So in some sense, if you are studying the smallest object, it tends to satisfy nicer properties than others. And surprisingly, we can even go a two-way direction here. We can show that, well, if you can inject A into the natural numbers, you will have that A is countable. Surprisingly, you can go the other direction as well. So what's interesting about this proof is that we've already proven this direction. We've already shown that if you can inject a set into a countable set, then the source must be countable. So to prove this side, that's all we need to do, right? Because to prove this side, we're done. We've proven it just now. We've actually used a result to prove this one. So what we need to do now is to prove the other direction from left to right. So we'll suppose A is countable. But once you have A being countable, you can find a set that contains it that is countably infinite, right? So there exists some A star bigger than A that is countably infinite. And this tells us, by definition, that there exists a bijection from A star into the natural numbers. I think I'm going to use A star to n in this situation because then we can do some injections. What this means is, by the way, here's a picture. So here's A, and it's contained inside some A star, and you can biject this guy into the natural numbers, which in some sense means that whatever goes from A into the natural numbers needs to be injective as well, right? So we'll define g from A to n by gx equals to f of x for x in A. And I'll leave you guys to check once again that g is an injection. And once you show that g is an injection, then you have found the desired injection, right? Because your goal is to try to find an injection from A to n. And you're good to go. So therefore, g is the desired injection. The idea is sort of whatever injective properties that g has will come from the fact that f itself is injective as well. So that's all the big picture. You can try to fill in the details on your own. Alright, I don't know how many results we have left to establish before we can go ahead to prove everything else from scratch. I'm really looking forward to proving all of those results in just a moment. So here's the idea. If A and B are countable, okay, we've already shown these results. We've shown that if you have the union of two countable sets has to be countable, or we've not shown this yet, we'll need to show this later on. We've shown that for any countable set, you can always find a countably infinite set bigger than that, which also tells you that you can have a set that's countable precisely when you can find an injection. You can inject it into the natural numbers. Now, of course, to prove this direction, we needed to establish the start results. So we still need to establish those. And it turns out that you can extend this idea of the finite union to the countably infinite union. It takes a little bit of effort, but the countable union of countable sets is gonna be countable. We're going to actually have to take some effort to prove that. It's not a very user-friendly result to prove, but it's really, really useful. So stay tuned for that. We are definitely going to prove that later on. A natural question to ask is, what about sets that aren't countable? Well, a set A is uncountable if it's not countable. I mean, Yes. If it's not countable, then it's uncountable, right? At least in English, right? And the idea is that sort of an uncountable set is bigger than a countable set. It's way bigger. So here's the claim. If a set B has an uncountable set A, then B is uncountable. So here's the result once again. Let's recall that we have A as a subset of B. Now it's A is like smaller than B. Again, we have not proven this result. We haven't proven that if this guy is countable, then the smaller guy must be countable. But if we have proven the result, which we will need to do, then taking contrapositives, if the smaller set is uncountable, then the bigger set must be uncountable as well. So it's basically, if a set B is an uncountable set A, then B is uncountable. I mean, yes, right? This is the contrapositive of B countable implies A countable. So that's literally it. And we have another interesting question, and that is if you take a set and if you take an uncountable set A and you get rid of a countable set B, then it sort of makes sense that whatever remains is still pretty big, right? So countables can be thought of as something that's really, really small. Uncountable is something just big. You can't even count it, right? It's really big. So if you take a big set and you get rid of a small set, intuitively, you should be left with a big set. It should still be pretty big. But how do we go about proving it? After all, we don't know much about uncountable sets. But we know a lot about countable sets. And in fact, uncountable by definition means not countable. So what if we proved by contradiction? So suppose for contradiction that A excluding B is countable. Now what does A excluding B look like? Well, let's draw a quick Venn diagram. A excluding B is essentially everything that is inside of A but not inside of B. So we can take the union, right? We can actually take the union. So we can take the union of A excluding B and B. We can take the union. And once we take the union of these two sets, well, we are actually getting, in fact, I drew this picture wrongly. Give me a moment. I just realized that, oh, no, actually, I think this is fine. I think this is fine. Okay, give me a moment. So, if we take the union of two countable sets, we are gonna get a countable set, right? This is from a result that, ironically, we haven't proved yet. But, we can also rewrite this as A union B. And A union B is basically everything. It must contain anything that's smaller, right? It has to contain its constituents. So A union B must contain A. And since the bigger set is countable, we must derive that the smaller set A is countable. But that's a contradiction because we've already seen that set A is uncountable, right? Contradiction. And the reason why is because A is not countable. It's uncountable, so by definition of uncountable, it is not countable. So, yeah, that's that. A excluding B has to be uncountable. That's surprising. I mean, it's not very surprising, but the proof is shockingly short, right? It's just, that's the proof. It's like, huh? Since when are proofs this short? Turns out, there are proofs that are short, and there are proofs that are long. And I've purposely left those for later, right? We have a few more results on countable infinity. So there was a result earlier on that what about the set of countable sets? Is it a countable set or is it an uncountable infinity? Well, here's the idea. If A is a countably infinite set and you consider all of the different possible subsets. Then, how many subsets do we get? It turns out that the number of these subsets has to be uncountable. This is actually a rather surprising result by the mathematician Cantor. I actually don't know how to pronounce his name, but that is a rather surprising result. And another surprising result, which shouldn't be very surprising, but it is a rather technical proof, is that if S is infinite, it must contain a subset T that is countably infinite. It's sort of like, well, of course, right? Because if countably infinite is in some sense the smallest infinity, then if there's any set which is infinite, it should contain a countably infinite subset. And we are going to prove that later on as well. There are quite a few gaps in our explanations that we are going to patch. Don't worry, we will get there. And what's interesting over here is that if A is an infinite set, then PA must be uncountable. So we're going to use these claims and whatever we've established so far, and any claim which we haven't proven, which we will prove later on, to establish this result. So let's first draw a picture, because a picture kind of helps. If you have a set A, then you can, in a sense, the collection of subsets of A, in a sense, should be larger, right? It should be larger, and in that sense, it should be significantly larger. But here's a problem. What do we know about infinite sets? Based on whatever information here, we only know that PA is uncountable, or let's do it this way. PA is uncountable if A is countably infinite. Right? So in the special case that A is countably infinite, then we know that PA is uncountable. And it's sort of obvious. I mean, infinite is bigger than countable infinite, so P of a bigger infinite set should be uncountable as well. It should be even more bigger, even larger. So how do we actually sort of argue this properly? Well, thankfully, we do know that A is an infinite set, so therefore it must contain a countably infinite subset. So let's just call this T, and we know that the power set of T is going to be countably infinite. So perhaps instead of doing it this way, here's our goal. Our goal is this result here, but let's not use this argument. Let's suppose that since A is infinite, it contains a countably infinite subset T. Right? So if A is infinite, it must contain a countably infinite subset T. And I want to show that the power set of T, if we can show that the power set of T is a subset of power set of A, then because the power set of T, if T is countably infinite, its power set must be uncountable. Then the smaller guy being uncountable means that the bigger guy must be uncountable as well. So all that remains is for us to establish this result. How do we prove that the power set of T is a subset of the power set of A? Well, it turns out we need to go back to the element chasing for subset, proving that one set is a subset of another. So we will fix the set, say, X in P of T. Then if X is in the power set of T, by definition, X by definition, X is a subset of T. And if X is a subset of T, and we know that T is a subset of A, then X must be a subset of A. But if X is a subset of A, then X lies inside the power set of A. And since any item in the left belongs to the right, the left side is indeed a subset of the right side. So we do in fact get this to be true, which tells us that PA must be uncountable. That's a very neat way, a very clean way to prove things. Right? So that's just a little bit of an introduction on countable sets and uncountable sets. However, we've glossed over many details. And now it's about time we prove them one by one. So let's go ahead to establish these results. Every other result that we've established so far are relatively low-hanging fruit. Once we manage to prove, once we prove what we have here, we get all the results that we have proven just now for free. Those are all simple corollaries of these larger results. And some of us have already seen the proofs for these results, but for the benefit of those who haven't, I'm going to reprove them from scratch. So here's the first claim. If the bigger set is countable, then the smaller set must be countable as well. So here is the proof. And we're going to prove it in this manner. So here is B, roughly speaking, and here is A, roughly speaking. Now, strictly speaking, B is countable, so that means it could be finite or infinite. And actually, we might need to prove both situations, but usually, countably infinite situations are easier to work with. Now, you might be wondering, I thought we had a heck. Now, we needed this result to prove that heck. So we cannot actually use the heck to prove this. So let's first start slow by supposing that B is countably infinite. Which means that you can find a bijection from N to B. Right? So that is the idea. Now, how do we actually go about this? Now, we know that A is a subset of B. We do know that that is going to be the case. So if this is B1, B2, B3, B4, the A's, each A is going to be equal to some B. We don't know what B is, but it's going to be some B. Right, so A2 is going to be some other B. Right, A1 is going to be some other B. We don't even know whether they're all in the same order or not. We just know that A is a subset of B. So what do we do here? Well, we have to think about how to sort of formalize this idea. Now, the sort of intuitive idea that I have is, well, if A is a subset of B, then I want to relabel the AIs, the different items in A, so that they sort of go in ascending order. Right, so that's the idea. And I need to think about how that works. So I think here's how we might go about it. So we'll write B equals to B1, well, that's in the spirit of computing. We're going to start with 0, 1, 2, 3, and so on and so forth. We're not going to start at 1, we're going to start from 0. So we'll write B as B0, B1, B2, and the idea is sort of that each BI is given by the bijection. Right, that's it. It's just a notational convenience. It's just a notationally compact way of writing it. In the math parlance, we call this a sequence, right? So that's the idea. So here's B. So we need to write, we write B this way. And we know that since A is a subset of B, for any x in A, we must get that x equals to Bj for some unique j in the natural numbers. Because it's a subset, so every item will have exactly one other guy. Okay, so that's sort of the idea that I have in mind. Now, what's the idea that that I'm going to sort of consider here? Well, I mean, I would like to prove my induction, but we need to work with infinite sets. So what we're gonna do is establish what we call an algorithmic proof, right? We're gonna define a new set. Let's call this S. We'll start off with the empty set. And the idea is that we're going to add in the BIs such that the BJs such that they belong to A. And so the idea is this, right? We want to sort of bring in all of the different B's, right, into this set S. And as we bring in the B's, we are going to label them one at a time. So we're going to define S to be the empty set, and we'll start with the index 0. I'm going to start at the index 0, and the idea that I have in mind is this. While, okay, so we have S being the empty set, and then we will call S is going to be the set of items we're going to collect. We're going to collect all of the items in S, and T is going to first take on all of the items in B. I is going to be sort of a counter that tells us how many elements we're adding in. So perhaps here's an illustration, right? So here's S. S currently contains nothing. T at the moment will contain B0, B1, B2, B3, so on and so forth. And for this discussion, let's first assume that the B1s and the B1 and B3 are items that were chosen. Maybe let's just say that B4 also lies inside the set A. Okay, so here's this thing. And what we're going to do is we're going to ask how many elements remains in T. Okay, so here's how we're going to fill up S. S is eventually going to hopefully equal to A, and I think we can do a quick proof of that. So here's how we're going to define the bijection. So we'll define I equals 0, and here's S, and here's the definition. While, and yes, we're going to use an algorithmic proof there, while T excluding S, T excluding S, wait, okay, well, T excluding S, right, is non-empty. Yep, well, T excluding S, intersecting A is non-empty. So in other words, if we've already transferred items over and it still overlaps with A, while this happens, so while we still get items in A, what we're going to do, we're going to take the smallest Bj, right? Well, okay, here's what's happening here. We know that while this happens, the set of, well, T intersect A is still non-empty. This will definitely be true, right? While this happens, it will be non-empty, which means that the collection of Bj's intersecting A, right, is still non-empty. So in other words, okay, so maybe we'll do it this way. If T exclude S intersect A is non-empty, that means there will still be some item in B such that it lies inside A. Right? If this fails, then there won't be any intersection between T exclude S and S. Now, I'll explain the excluding S in just a moment. So what we can do here is, since there is a Bj such that Bj is in A, the set of indices is non-empty. Right? It is a non-empty subset of the natural numbers. And if it is a non-empty subset of the natural numbers, we can use the well-ordering principle. By the well-ordering principle, right, we can, the B, there exists some unique integer, we'll call this K naught, Ki, we'll call this K sub I, inside the set, right, inside this set, which is the minimum, right? It's the smallest possible number. And so we can now define A sub Ki, right? A sub Ki to be the first item that we're going to throw into equals to, A sub I, sorry. A sub I to be equal to B sub Ki. We're going to include S. We're going to now throw in AI into S. And then we're going to increment I to I plus 1. So what's the picture here? So here's the algorithm. If I equals to 0, we'll run through all of these guys and see which one goes into, whether this guy is non-empty or not. Right? So in this situation, B1 belongs to A in our mock setup. So we're going to add B1 into S and give it a new name called A0. It's going to be A0, it's a new name. We're going to do that. And then when we take T exclude S, we're basically going to strike out this term, right? T exclude S means this set getting rid of anything in this bottom set. So in the bottom set, we have a B1. The idea is we're going to get rid of this guy. We're going to kill this item. And then in the next increment, when we increment I to the next number, so it starts with 0 and then 1, we'll once again run through all the items here. We'll take the smallest indexed B and put it into S. This will be our new A1, and then we're going to kill B3 from the set T. Alright, so that's sort of the idea there. So maybe I can define it this way. While T intersect A is non-empty, we'll define S to be that, and then we'll define T to be T excluding AI. And it's the same formulation, right? And then we'll increment and then we increment I to I plus 1. And then we can keep going. So once again, we can scan through all the items here. And then B4 is the one that's now being sort of targeted, if you would. It's being targeted. So we're going to add B4 into the set here. We'll call this A2. And then we'll get rid of B4. And we'll just keep going. We'll just keep going until we are done. So there are technically two possibilities. Could we ever be done? Well, if A is countably infinite, then we probably will never be done. But if A is finite, then we will be done. So we have a few possibilities here. Right? So here's our sort of algorithm. At the end, what we will get, we will obtain S to be the set A0, A1, A2, so on and so forth. And we have two situations to think about. Firstly, right, T intersect A equals to empty set eventually at some point, right, at some point in time, versus T intersect A being non-empty at any point. That's the question, right? So either we will eventually get an empty set, or it will never be empty and they will always intersect. In the first situation, we will define h to be the bijection from the natural numbers to a via, well, sorry, this is the second set for the countably infinite case. If n, we'll define h from n to a via h of I equals to ai. Right? So in other words, for the natural number 0, we'll map it to a0. For the natural number 1, we'll map it to a1. For the natural number a2, we'll map it to a2, and so on and so forth. We are always going to be able to get some number. And the number, by this condition and by whatever we've done so far, is going to be unique. So we're good to go. You can prove that if you wish, but this is the key idea. And finally, if t intersect a eventually gets empty, then there exists some, say, m, I equals to, there exists some m in natural numbers such that when I equals to m, t intersect a equals to empty set. Either this is a situation or the negation happens. And that tells us that we can define h to be the bijection from 0 all the way to m minus 1? All the way to m minus 1. Yeah. This will mean equals to ai once again, well, awkward, a via h of I equals to ai, which is once again a bijection. You will always, it's a well-defined function, it's injective and it is surjective. And so that's how we prove that, well, if we can find a bijection from either a finite set or a countably infinite set to A, this tells us that A is countably infinite. A must be, well, not countably infinite, but it has to be countable. In either way, A is countable. Right? Now, my pen is gonna die soon, but we are going to at least sort of resolve one more part, which is this question, right? So we've shown over here that if the bigger set is countable, then the smaller set must be countable. So here's the next question. If B is finite, then A must be finite. And it makes intuitive sense. If the bigger guy is finite, then the smaller guy has got to be finite. But how do we justify this situation? Now, we can actually run through this algorithm, but we must try to argue that this is impossible for the finite set situation. So we can actually run through the entire process, and now we need to ask this question. We need to define H to be this situation. So now what happens if B is finite? That means there exists some natural number n, right, such that, well, the argument is slightly different, right? Let's write that again. There exists some n such that we can write B as B0, B1, all the way to Bn minus 1. Correct? However, if this happens, then we do get a bijection, right? Then A is going to be equal to A0, A1, all the way to An minus 1, An at some point in time. In fact, it keeps going, right? It actually keeps going. Oops. So we do know that it has to, so we do know that it keeps going. We do know that it keeps going if B is, well, if A is infinite. And the idea is sort of that you can't really inject this way. You can't really inject it this way, right? But perhaps we need to properly establish this claim. And after this, we'll have to go for a short break because my pen needs to recharge one more time. So here's how I might do it. I might not even consider A is sort of everything, but we can just consider this small set over here. Right? We can consider this smaller set. And we know that A is a subset of B, right? So therefore, this set has to be a subset, well, this whole thing is not all of A, but whatever it is, if A is a subset of B, then this whole thing is a subset of B. Therefore, we'll get B0, B1, Bn minus 1. Now, once we have a subset, we have a very natural injection. We'll call this set A naught, and it's given by inclusion. The idea is this, right? If I were to define f of x to be just itself, then it must lie inside B, and we do get an injection. Right? We will definitely get an injection in this manner. Now, once we have an injection, this tells us that the number of items here has to be smaller than or equals to the number of items here. Right? We've seen this the other time. If we can inject from a smaller set to a bigger set, then the bigger set has more items. In particular, A naught has n plus 1 items, and B has n items. And therefore, n plus 1 is smaller than or equals to n. And I think you can see where we're going with this. We do get that 1 is, well, 1 is smaller than or equals to 0, but 0 is smaller than 1, so we get a contradiction. And this tells us that if B is finite, we must get A is finite. Right? We must get that A is finite. Now, if B is infinite, we have no idea whether A is finite or not. We have no idea. We do know that if B is countable, then A must be countable. But if we know that B is finite, we know that A is finite. But if we know that B is infinite, we know nothing about A, because B is too big, right? So we'll go for a short break while this thing charges. We'll be back at 9:20, and we'll go ahead to prove everything else. This is probably the first of the technical proofs, so feel free to watch this stream again if you want to sort of absorb the ideas behind this proof. Alright, welcome back everyone, and we are gonna continue and sort of just recap and rehash what we did just now. So we've basically shown this statement, we've proven this claim that if you have a bigger set and the bigger set is countable, then the smaller set must be countable as well. And we've also shown that if B is finite, then if the bigger set is finite, then the smaller set must be finite. Here's just a quick diagram to sort of illustrate the picture. If B is countable, then A is countable. If B is finite, then A must be finite. And the quick proof is that we list out the items in B and we slowly add them into the items of S one at a time. We eliminate after each addition. What remains is a bijection from the natural numbers to A, and everything works out. That's the key idea. We basically take all of the items in B, we throw them into this new set called S, and this collection of S's is actually in fact going to be equal to A. Right, so you can do a quick check that that's the case as well. Alright, so that's the rough proof. Now with this in mind, we can now go ahead to prove countabilities using injections. And that's what we've been waiting for, right? We actually really want to do this. So here's the result which we still need to prove, that we are required to prove. We actually haven't proved this yet. If we have two countable sets, then the union of two countable sets must be countable as well. Now here's a very quick picture. So imagine, well, not imagine, but we have the natural numbers. Now we can't use the integers because we actually used this result to show that the integers are countable. So in the way that we've set things up, we don't want to use integers. What we do want to use, however, is something a bit more clever. This one is given by my student, Junhui, if you're watching this. Thanks for the proof, I'm going to use it. You actually have the even integers and the odd integers. Like this. And the idea is that you map each of these guys to A, well, you map each of these guys to A and each of these guys to B. So that's the idea, right? So you sort of take the even numbers, you throw it to A, you take the odd numbers, you throw it to B, or the other way around, you can inject it into N as well. And then you show that we get an injection that works out. So once you can inject this guy into the natural numbers, we get countability. So let's go ahead and prove that. Now, we know that based on what we've seen just now, the collection of even integers is countably infinite. And you can quickly check that if you have two sets that are countably infinite, you can always find a bijection between them. We go back to the definition of countably infinite being a bijection with the natural numbers. Here's a very quick proof sketch. If you can biject this way, then you can biject. If you can biject this way, you can biject this way, because the inverse will be a bijection. You can biject this way, that still works. So since 2n is countably infinite, we can find a bijection from A to 2n. 2n is just our abbreviation for the set of even numbers. And similarly, since 2n plus 1, that's our odd integers, is countably infinite, there exists yet another bijection from G to the odd integers. And we note that the natural numbers as a whole is the union of the even integers and the odd integers. Well, odd non-negative integers and the even non-negative integers. We can define the function h from the union, right? So in some sense, A is going to end up over here, A is going to end up here, while B is going to end up here. In this manner, the A's and the B's also don't intersect one another. So that's a really, really clever way to deal with it. Now, of course, we are making a very okay. We actually made an assumption here. We had to make an assumption here. Okay, we're actually making an assumption, right? We assume that A and B will always get thrown to a different number. However, A could intersect B. It's entirely possible. So let's just first plug that little patch over there. Let's assume that A and B don't overlap. We will come back to this assumption later on, right? And furthermore, we are bijecting it all to 2n and 2n plus 1. So we are also assuming that A and B are countably infinite. This is not off to a good start because we need to consider countability later on, right? And countability could mean finite or infinite. So this might be a bit concerning, but thou shalt not panic. Don't panic. We'll get there. Okay, we will get there. Okay, so let's first work with the countably infinite situation. We're gonna sort of bootstrap all of this to get the finite situation later on. So H will be the mapping from A union B to the natural numbers defined by H of x equals to, well, either x belongs to A or x belongs to B. If x belongs to A, we're gonna follow the instructions from F to the even numbers. And if x belongs to B, we're gonna follow the instructions from G to the odd numbers. Now, what do we need to check? Well, we need to check that H is an injection, right? Because if we can inject into N, we're good to go. That's the idea, right? If we can inject into N, then we can prove whatever we need to prove. So let's try to prove that. Even then, we still have a bunch of assumptions we need to take care of. So we're gonna have to work with that. But for now, let's just deal with H. So we're gonna claim that H is injective. Again, we don't have to care about surjective. And if H is injective, well, or at least that's our claim, then we do get, this implies that A union B being the source set, since we can inject from the source to the target, and the target is countable, then the source must be countable. Okay, now let's proceed with H being injective. Let's hopefully prove this claim. How do we prove this claim? We'll first start with two inputs in A union B, and we'll suppose that the outputs are equal to each other. Right, we're going to suppose that the outputs are equal to each other. At this point in time, it might feel a bit, oh, what are we supposed to do now? Well, we do know that x1 and x2 could have belonged to A or B. So why not let's just work with what we have, right? So let's work with a bunch of situations. Suppose x1 is in A, x2 is in A, x1 is in A, x2 is in B, x1 is in B, x2 is in B, A, x1 is in B, x2 is in B. We don't know where x1 and x2 are, we just said that they belong into the union. But we know nothing about which part of the union they belong to. So, if they belong into A, then h of x1 and h of x2 are equal to f of x1 by our definition. If x belongs to A, we'll follow the instructions from F. And if x2 is in A, then we follow the instructions in F as well, which gives us x1 equals to x2. And that's great. Now, surprisingly, you can also derive a similar result when x1 and x2 both belongs to B. And you can maybe check that on your own. Well, what happens if x1 is in A and x2 is in B? Then well, h of x1 is going to be defined by g of x1, because, well, sorry, f of x1, apologies. And h of x2, if x2 belongs in B, will be defined by g of x2. So what we do know is that f of x1, if we look at f will throw anything in A to a collection of even numbers. So f of x1 is even. And g will throw any item in B into the odd numbers. So g is going to be odd. Well, g of x2 is going to be odd. So we are going to get a situation where the even number equals the odd number. That's a contradiction. And likewise, for this situation, you will also get another contradiction. So these two situations are actually impossible. They actually cannot happen. But for the remaining situations, we do get x1 equals to x2, and therefore we can conclude that h is injective. That's within our purview. And since h is injective, then we have that, well, A union B is countable. Except that we are working with two assumptions here. We're actually working with the assumption that they don't intersect, and we're working with the assumption that they are countably infinite. So, how do we deal with these results? Well, here's the idea. Okay, if they are finite, we can still get these guys to be injections. We can still define them to be injections. So maybe I'll do a quick explanation for A being finite and B being finite, or at least A being finite and B being infinite. So what happens now if we're now working with a situation that A is finite and B is countably infinite? Then we can still try to define, well, A can be defined, well, the function from f to the even integers can be defined in this way. So now we're assuming A is finite, right? So we can't really use bijection, but we can define it in this way. So since A is finite, well, okay, fine. Let me just fill up the details here. So since if A is finite, then there exists a bijection f, well, we'll call this f naught, from A to the non-negative integers for some n. The idea is that we can sort of biject A this way, and then we can biject this set into, well, the collection of even integers. And this is going to be a subset of the even integers. So what this tells us, here's the trick. The trick is that we can biject this way. We can biject this way, and then this will be our bijection. We'll call this f from A to the finite even integers. This will still be an injection into 2n. This will still be an injection. It still works. And if it's an injection, all of these arguments over here at the bottom, all of these arguments here will still work. In fact, what we're going to do is we're going to sort of clean up the bottom, because we've already established that based on our construction, H must be injective. Okay, so let's clean this up. And now we have a little bit more space to sort of present our arguments. So let's just bring this part over. Perhaps we can elaborate on the A business over there. Let's do some elaboration rather than keep everything so squeezed up. Well, we can define, we can call this one F0, and we can define F to be from A to 2n by f of x equals to f0 of x, x in A, and we can check, we'll leave this as an exercise. F is injective. And if F is injective, we can still show that how we define H, that is still going to be injective. We will still get countable. Now the fun thing happens here, if G, or rather if B is finite as well. So we still need to consider the case. What happens now? So we've already looked at a few situations. We've looked at the situation when A and B are both countably infinite, and we've looked at the situation that A is finite and B is countably infinite. So here's the situations we've checked out. So we'll let C represent countably infinite and F represent finite. We've checked the situation when A is countably infinite and B is countably infinite. We've also checked the situation when A is finite and B is countably infinite. This is basically this situation over here. We also can check by just doing a relabeling the same argument for A being finite and A being countably infinite and B being finite. And something interesting happens in this last situation. Something very interesting happens. So it's pretty cool. Now let's now assume that A is finite and B is finite. Right? By the previous argument, right, we have shown that there exists an injection from F, well, there exists an injection from A to some subset of natural numbers. Right? This is a finite subset. By the same reasoning, you can find, oh, this is an injection. Here we go. You can find an injection from B to the odd integers. Right? By the same logic, you can just follow the same argument. You can find a bijection to a finite set. You can transform that to the odd numbers, and you can find an injection. But what's interesting now is that H is not just an injection from A union B to N. It is an injection to a finite set. Instead of N, we're now going to replace this with 0, 1, 2, all the way to the larger of the two numbers. The larger of the two numbers. So you have an injection from A union B to a finite set. If you inject to a finite set, you must get that not only is A union B countable, right? In every other situation, it's countable. In fact, it's countably infinite. you even get the fact that A union B must be finite. So in all the other situations, you can check that it's going to be countably infinite. And yet, if both sets are finite, the finite union of finite sets must be finite. And it does make sense, right? If you take a set and you take another set, you smash them together, you're going to get a union of finite sets. So that sort of makes sense. But it's nice to see it arise from the proof for the countable set situation. Right? Once we establish this proof that the union of two countable sets is countable and the union of two finite sets is finite, we get so many properties. Now, we actually use this to establish the countably infinite hack, which is to say that if A is countably infinite, then you can find a set bigger than A. Well, if A is countable, if A is countable, whether finite or infinite, you can find a set A star that is bigger than A that is countably infinite. Right? We can use this result to actually prove this result over here. So that's pretty nice. It's a pretty cool result there. Right? So we've done it. We've actually proved this result, and we can now use the countable set hack. But we're left with one more. Problem. There's just one last detail which we haven't checked yet. We've always assumed that A intersect B is empty. Let's clean up the board and summarize what we have discovered so far. So far, what we have proven is that if A and B are countable, then A union B is countable as well. And furthermore, we've actually also proven that if it's finite, then this guy is finite. But we were always working with the situation that A and B don't intersect one another. In other words, we're working in the situation when A and B don't intersect one another. If they don't intersect and you take the countable union, you take the finite union of two countable sets, you get a countable set. What happens if they do intersect? Like this. Well, if they do intersect this way, we have a trick up our sleeves. So, suppose A and B do intersect. So now we're claiming that if we remove this condition, we still get a true result. So suppose A and B do intersect, we're gonna write A union B as the disjoint union of A and B. So instead of thinking of A union B as A union B, we're thinking of it as A union B. In other words, A union B. And this time the union is disjoint. Right? It's disjoint. But we know that this guy is a subset of a countable set. So therefore, this guy must be countable. A subset of a countable set must be countable. And B is by hypothesis countable. So now we have a situation where we have the union of two countable sets that don't intersect one another. We can actually use this special case to conclude that this whole result is still countable. And that's the trick there. That's the disjoint union trick, a very useful trick in mathematics. So finally, with all that hard work done, we can finally, with confidence, say that the union of two countable sets is countable, and the union of two finite sets is finite as well. Feels great. Now we do have a few more countability results, so it feels a bit strange that if you look at the different questions, we actually cover a lot more questions in like 1 hour. And like in the 2 hours, we are covering like only a few questions, like a handful of questions. But these are not say the easiest to prove, right? So they do take a bit of effort to prove. So my understanding of examinations is that in general, we're not really required to reproduce the proofs, but we do want to actually use the results, which is basically the first half of this live stream, right? So it's sort of showing you how to use the results. Okay, here's a tricky one. This one took me a lot of effort. So we'll be here for a while. Strap on your seatbelts and we are ready to go. So now, suppose now we have a countably infinite union. Then we claim that a countably infinite union is countable. Well, this seems rather daunting and honestly will take a little bit of effort. We can actually use the same trick that we did just now. And the first thing we're going to do is actually assume that all of these guys don't intersect one another. Right, that's the, they don't intersect one another. Correct. So the idea is sort of we consider them as not intersecting one another first, and then we'll sort of deal with the intersecting case later on. Now we're looking at the countable union of a bunch of items. So if they don't intersect, we're actually in a very good place. And here's sort of the idea that I have at the back of my mind. Okay, so let's just do it this way. Here's n cross n, and we're gonna take a countable union. So I'm gonna let each of these columns, you can call this the x equals to 0 column if you would. If you want to call this the x equals to 1 column, you can as well. The x equals to 2 column. Oops. And so on and so forth. But more importantly, what I'm going to do is that the idea is that if each of the AIs are countable, then we can sort of put them along these lines. We're going to put them along these lines over here. Okay, we're going to put them along these lines. Now I'm going to assume one more detail. Alright? And we're going to assume that they're all infinite. We're going to first assume they're all countably infinite. And we're going to use the countably infinite hack later on. But for now, the idea is that if they're countably infinite, we can sort of arrange them all on this lattice point over here. And the idea is sort of we want to inject this set into n cross n. We know that n cross n is countable, so our goal is to find an injection from the union into n cross n. That's the goal. Because if we can find the injection, we can inject into a countable set, then the source set has to be countable. And here's how we're going to define that. The idea is we're sort of going to line them up this way. This is going to be the item A00. The first 0 indicates that it's from the set A0. And then you have the item A01. And then you have the item A02, you have the item A03, A04, A05, so on and so forth. Now in the second column, we're going to get, here's the idea, A10, oops, A11, A12, A13, A14, A15, and so on and so forth. And then we're gonna have B20, well, not B2, so what am I doing? A20, A21, A22, A23, A24, A25, and so on and so forth. So that's the idea behind our proof. Now, here's how we're going to let all of this be airtight. So fix J in the natural numbers. and then we'll consider the set AJ. Since the set AJ, so let's just say we have a column here that represents AJ. Since AJ is countably infinite, and don't worry about the finite case, we're going to use a hack to settle that. Since AJ is countably infinite, there exists a bijection, say g of j, from AJ to the natural numbers. Now I'm thinking to myself whether it makes more sense to biject this way. I'm going to biject from n to AJ. I think this is a slightly more clever option over here. Alright, so what we can do here is we can write for each, I think I should use I, sorry, I should use I over here. Ooh, darn it. We should use I. Yeah, okay. So the idea is that is the ith set. So then for each natural number j, we can, there is a unique, we can write aij to be a shorthanded abbreviation for gi of j. Now gi of j is a legitimate, well-defined expression. It's a function, it's a bijection. It works out well, so we can write aij in this manner. Right, we can write aij in this manner. And once we write aij in this manner, then it seems pretty straightforward what we need to do. We will define the function h from the union, and to disambiguate, let's just use a different letter, k over here. We'll define h to go from the union into the natural number, no, we're into n cross n. How are we going to define this function? We're going to define it by h of x equals to ij if x equals to aij. Right, so the idea is sort of, we throw the aij component, the term, say over here, say j, this will be aij. We'll throw the aij elements onto the point ij. Right, that's the sort of the idea over there. Now, the problem with this definition is, how do we know it's a legit definition? How do we know that this definition is indeed a legitimate one? We first need to check that this is a legitimate definition, right? So we'll need to first verify that this expression is well defined. In fact, we need to check a few things. H is 1, well defined. And secondly, it is an injection. So that's sort of the idea here, like, wait a minute, how do we even start? Well, here's the proof. To show that it's well defined, we need to show that every input has at least one output, and every output has at most one input. Every input has at most one output. So we'll fix x inside the union, and it turns out that we don't really have to worry too much. The reason why is because x is in the union. This tells us that x lies inside ai for some I, but the ai and aij's cannot intersect, right? That was our assumption over here. We assume that they don't intersect, and therefore we can say that it is in ai for some I, and not in aj for j not equals to I. So we can rephrase this to mean that there exists a unique I such that x lies inside ai. It's unique, we don't have to worry so much. But if x is in ai, then we know that gi is a bijection, right? So x being in ai, if gi is a bijection, we can find some input, right? So since g is bijective, there exists not just an input, but a unique input, because it's a bijection, it's not just a surjection, it's a bijection, such that gi is bijective, gi of j equals to x. And it's all unique, which means that x equals to aij is unique, and that tells us that h of x must be uniquely equal to h of aij, which equals to I of j, because we're mapping the point aij to the coordinates, to the two-dimensional coordinates. So it's a really, really clever proof. I didn't learn this on my own, but I got it somewhere, and it's a pretty amazing result. And okay, so we've proven that it's well defined. Now we just need to show that it's an injection. This shouldn't be too difficult, because if h of x equals to h of y, then we can say that h of aij equals to h of ars, just without loss of generality, which means that ij equals to rs, but that simply means that I equals to r, j equals to s, and therefore aij equals to ars. It's the same, I and j, I is equal to r, j is equal to s, so aij must equal to ars. And what that means is that if the outputs are the same, implies that the inputs are the same, then h is an injection. And if h is an injection, then we have injected into a countable set. So therefore, the source set must be countable. But we're not there yet. We're not there yet. We actually imposed a few assumptions that made our life a lot easier. So let's sort of clean up the board and tackle those assumptions. So we've proved this result under these assumptions. We're going to call this condition 1 and condition 2. We've proved the result under these two conditions. How can we slowly relax these conditions? That's sort of the first train of thought here. Now we are first going to relax C2. C1 is going to be a relatively easy relaxing. Let's first relax C2 and then we can relax C1. So now we're going to claim that the result R is still true if we relax C2. And here's the idea. In other words, right, now we don't assume that AIs and AJs don't touch each other. So, sometimes they could intersect, sometimes they can't intersect. We are going to use a trick that we did just now. So previously, we proved this result, right, by decomposing it into a disjoint union. That's the trick, right? That is the trick that we're going to use. So we're going to define, let's prove this properly. This is called a disjoint union trick. We're just going to generalize this to a higher number of sets. So we'll define B0 to be equal to A0 and Bn to be the following set. It's going to be An excluding the union of everything else that came before it. So the idea is sort of, we're going to consider A0 and then A1 excluding A0, and then we'll consider A2 excluding A0 union A1, and A3 excluding the triple unions, and so on and so forth. So that's the idea. That's sort of the idea that we have here. Right? We're sort of defining it this way. Then we have to make another claim here, right? We actually need to claim this. So claim the union of the AIs is equal to the union of the BIs. It's the same union, but this time the BIs and the BJs don't intersect one another. And we've seen that this guy, since each of the BIs, okay, so here, let's just write out the full argument first. So since each BI is a subset of AI which is countable, this is a countable union of countable sets with the added property of the disjointness. And we've seen just now that if we get a countable union of countable sets, the union is countable. But this simply means that the union of the AIs is countable. Now we have to prove this claim. We need to actually go ahead to prove this claim. We haven't proved this claim yet. We need to go ahead, prove this claim, and make sure this claim is legit before we can use it in order to conclude. That being said, let's put an asterisk here and show how after we relax C2, we can relax C1 and still get the same answer. So now we're going to assume that C2 doesn't always hold. And now we're also going to assume that C1 doesn't always hold. So in other words, each of these A0s are countable. We don't know whether they're countably infinite. Well, we do know that if for any countable set, you can find a countably infinite set that contains it. Alright? So A0 is contained in A0 star, which is countably infinite. A1 is contained in A1 star. A2 is contained in A2 star, and so on and so forth. This means that the union of the countable sets is a subset of the union of the countably infinite sets. And we've seen from what we have proven just now that the union of the countable union of countably infinite sets is countable. And the subset of a countable set is countable as well. So how do we do the general case? We sort of embed it in a sense to a countably infinite set. But now, we still have some work to do. We're not done with this proof yet because we still need to claim this guy. This is our last piece. And then we can move on, and we still have a few results left. So this is going to be fun. So we are going to continue by proving this claim. We're going to prove this claim given the definition of B0 and A0. So let's, we have two claims to prove. We have claim, we call this result 1 and result 2. Let's first prove result 2 because that might be a little bit easier for our purposes. Now for result 2, we know that BI intersect BJ is a, well, we want to prove that they are empty set, right? We want to prove that they are empty set. So the idea is we want to try to show that they are a subset of an empty set. So, and more precisely, when I is not equals to j. So, how do we start? Well, since I is not equal to j, let's suppose that I is smaller than j without loss of generality. The idea is sort of j is going to be defined in such a way that it excludes I. That's sort of the idea. So, bi intersect bj. Bj is sort of like bigger. So this will be equal to bi intersect bj is going to be defined by ai excluding the union, well, sorry, AJ, excluding the union of everything that came before it. Correct? But this thing over here, if you look at the definitions of the BIs, this is going to actually contain BJ. This whole thing is actually going to contain, this whole thing is going to contain BI. Right, this is actually going to contain BI. Let me write it down properly. Darn it! Right, it's actually going to contain BI. So this is going to be it's going to be a subset of BI intersect AJ excluding BI. And if you intersect with something outside of you, you get an empty set. And the left side is an empty set. So we can conclude with all of that BI intersect BJ is the empty set. It has to be empty. I mean, there's no other possibility. So that's R2. And for R1, we need to prove an equality of sets. Right? So it's R1. Let's try to prove R1 here. I think based on the definition here, it's quite straightforward to see that BKs are always a subset of AKs. That's definitely going to be the case, which means that the unions of the BKs will be a subset of the union of the AKs. Now to go in the other direction, because we need to prove two-way inclusion. So suppose we want to now prove. Okay, so proving this direction, it was basically over here. So that's basically done. Right? Now we need to prove in the reverse direction. So now let's slowly try to go about it. We'll fix X in the union of the AIs, the AKs I mean. And what it tells us is that X lies inside A sub say M for some natural number M, and because it lies in some M, the collection of integers L such that X lies inside AL is non-empty. And this tells us, by the well-ordering principle, yes, we're going to use the well-ordering principle again, and we're sort of reducing it to the smaller situation here. Okay, that's the idea. If X belongs into AM, it has to belong into some smallest AM, and well-ordering principle helps us bootstrap the argument. So by the well-ordering principle, there exists some minimum, say L naught, such that X lies inside A L naught. But that means that for any index that's smaller than L naught, X cannot lie inside AK. And what that means is that X must lie inside AL naught and none of the other AKs. But this is basically equals to B of L naught. And if it lies inside some B, it must lie inside the union of B's. So we've taken any item in the left, right? We've taken any item in the left and shown that it belongs to the right. And that's how we do it. That's a long argument. So sort of to wrap up what this part, well, we've shown that we can write this as a disjoint union, right? And to show that it is a disjoint union, we first needed to show disjointness, which is relatively, disjointness means it's relatively not too difficult. And to show the union, it takes a bit of effort to go from the A case to the B case. We needed the well-ordering principle to help us sort of bootstrap our argument. The idea is that if X is in some AM, then you can find the smallest AM that contains it, in a way, right? So the well-ordering principle helps us make that concrete by establishing a minimum L0. Why minimum? Because anything lesser, and the guy's not in there anymore. So that the minimum there really helps us sort of obtain information that we might not get if we do not impose the minimum requirement. So it's a rather long argument, but that's it. The countable union of countable sets is still countable. Alright, so that's that. Okay, we have a few more results, and these are big famous results in set theory and infinite sets and all that. But let's just take a look here. So any infinite set contains a countably infinite subset T. Now, the irony over here is that we are going to basically argue the case just like we did with one of the previous results. So we can run the same algorithm. So we can run an algorithm proof again. So the idea is this. Here's S. You have many things. And T, you can slowly plug these things and put it into T. And the idea is that it will never ever run out. Right? So the idea is that S cannot run out. If it runs out, then it's gonna terminate somewhere and it's gonna be finite. So here's how we're going to define it. So we'll define once again. Perhaps we'll call this we'll call the target set. Eventually we'll call it B. We'll call this A. So we'll define A. We'll initialize it to be S and B to be the empty set. And then we will say this, while A excluding B is non-empty, we're going to take any item you want, right? So I think while A is non-empty, if I'm right, while A is non-empty, we'll let B, we'll include, well, there exists some item in A, right? Because A is not empty. And then we can include this item into B. We can put a counter. We can run a counter. So let's run a counter I equals to 0. We can define, in fact, we can define it this way. Whoops. We can define Bi to be by definition equal to this non-empty where this element, because A is not empty, we can include it into the set B. I think it's supposed to be T technically, right? T, whatever, it's not that important. And we can increment I by one number, right? So once again, the idea is that you can throw in an item here and then you eliminate it from, oh, we've got to eliminate it from the item. So let's do that. So A will be A excluding B, right? We're going to throw away anything that belongs to B. In fact, we can just throw away Ti. That's good enough, right? And then what we can do is, well, the idea once again is that from the first item, you're going to say, choose this item, this is going to be T1. You're going to put it into T1 and then you're going to cancel it away from S. Right? That's sort of the idea. T2, T2, and then cancel away from here. And you can repeat. And each of the items are going to be distinct, so you don't have to worry about injectivities and whatnot. So we can define H to be the mapping from the natural numbers to T by H of I equals to Ti, right? And we claim that H is, well, let's write that properly. We claim H is bijective. And I'll let you guys check that it's injective. You don't have to worry too much. The argument is not too bad. H is injective. In fact, let's just do it quickly here because it might get a bit long. And the reason why is because, right, for I not equals to j, okay, the reason why, let's just do it this way, H is injective because when I is not equals to j, we can say that I is, say, smaller than j. This implies that by our choice of our options, Tj will be inside a set, right? Inside some set, T1 ... to Ti. So therefore, Ti cannot be equal to Tj. But that means that H of I cannot be equals to H of j. Right? So if I is less than j, then these two items cannot be the same, and therefore H must be injective. Different outputs give you different inputs. Works out well. Now to check that H is surjective is a little bit tricky. So H is surjective. Right? And how do we sort of explain this? It means that for any item in T, you can find an integer that goes there. So we need to show, our goal is to show that A is always non-empty. If it somehow becomes empty, then we'll have to stop somewhere, right? If A somehow becomes empty, we have to stop somewhere, and we must conclude that the source set is finite, which is a contradiction. To argue the case is, suppose there exists some there exists some natural numbers such that A equals to empty set. Then we can check, we can sort of run through the argument again to show that S must equal to T. Oh, I start with 1. I should have started with 0. Darn it. T0, T1, Tn, which is finite, which is a contradiction. This means that A is always non-empty, which means there always exists some integer k such that Tk equals to H of k. And we're good to go. So in other words, you can keep adding things into T. Right, so that's the argument there. That's the argument. That was a long argument, and we are almost done. We are almost done, and we have finally come to the final result, which was actually the result that was asked in the chat, which is, what about the power set of a countable set? What if you consider the set of countable sets? Turns out that it is uncountable. So this is the claim, right? So let A be a countably infinite set. We must get that PA is uncountable. So here's the proof, and it's a very, very clever proof. I'm just amazed when I first saw it. So again, we know nothing about uncountability, but we know a lot about countability. So let's suppose PA is countable. Let's suppose that PA is countable. Now if PA is countable, then you can find a bijection between two countable sets. Right? You can find a bijection. You can always throw items from A into PA. It's always possible, and it's always bijective. If PA is countable, you're gonna see why that condition is so important, because we're going to get something that's rather crazy. So we're gonna define a very crazy set. We're gonna define the set of S to be we'll define S to be the collection of items in A, okay, such that, okay, what does it mean? When we say that F is a bijection from A to PA, it means that f of A is a subset of A, right? F of A is an element of PA, which means that f of A is a subset of A for any element A. Okay, this is gonna be true because f is a bijection from A, is a function from the set A to the power set, so f of A is going to be a subset of A. So we're going to define S in this manner. We're going to define S to be the subset of A such that X does not belong to f of X. Now, all the items in S here belong to A. They all belong to A. It works. So this whole thing is actually a subset of A. But that means S is an element of the power set of A. And we've already established that F is a bijection. So for any item in the output, I'm going to write it this way, any item in the output, you can always find some input. Maybe we'll call this small s. You can find some input, right? So in fact, it's a unique input. So there exists a unique input S in A such that at big S, big S is equal to f of little s. Now here's the little troublesome fact, right? Here's a slight troublesome fact. Okay, by the way, it's not in f(x), right? Here's a troublesome fact about this reality. Okay, so what does this mean? Well, S is either, the element S either belongs to S or not. One of these things must be true, right? Either it belongs to S or not, at least for sets. Now if S belongs to S, that means S belongs to f of S because that's the definition of S. But if S belongs to f of S, then the statement S does not belong to f of S is false. Right? And if it's false, then it cannot belong in S because all the items in S are the elements such that this thing is true. If it's true, we put it in. If it's not true, we just heck it, right? So we've shown that if S is in S, it cannot be in S. That's a contradiction. And you might be thinking to yourself, oh, that's simple, then S is not in S. But if S is not in S, then S is not in f of S by the definition of f. Which means that S is not in f of S is true. That means that S is in S. So if S is in S, then it's not in S. And if it's not in S, then it's in S. You're getting a contradiction on so many levels here. So you're getting a contradiction of both levels. So what does that mean? We follow the logic. The only problem is that we assumed that PA is countable. Therefore, since we contradicted PA being countable, we can conclude that PA is uncountable. And there's that. Took a bit of effort. It was rather amazing. This is actually what we call, we actually gave this a name. This is actually called Cantor's diagonalization argument. And he sort of proved this result in the context of infinite strings of natural numbers. Decimals, if you would. So it was a very clever proof. It was a very clever proof. I was amazed when I saw it. The definition of this set is like, wow, who would even think of this set, you know? So, with all that hard work done, we have now finally proven everything that we needed to prove to establish our countability results. In the next stream, when we talk about counting, we're gonna go back to finite sets. So all these brain twisting things, it's not gonna be there. It's a different kind of brain twisting with counting arguments and all of that. This is a taste into real analysis, so I do intend to cover real analysis in May and the summer season, right? So with all that being said, see you guys in the next stream, and I'm gonna make sure I'll charge my Apple Pencil prior to the stream. Alright? Good day.